we are going to give you a brief introduction to the concept of limits, which is one of the first things you're going to learn when you move on to your calculus class. So, our class is titled Pre-Calculus, so that's the whole point of us to get ready for calc. So, a couple of the concepts we're going to talk about today are not necessarily on your final, and that's the only time I'm going to test you for our class. But I still want to introduce you to some other topics, even though they're not being tested. But, like I said, it is the first thing you'll talk about when you go on to calc. So we're going to be estimating the limit at a certain value for a function. And we've seen discontinuities before, like holes and asymptotes and jumps and oscillations. And that doesn't mean we can't figure out what's called the limit. So we've actually seen a lot of what we're going to discuss before in terms of end behavior and where the function is approaching. And that's really the same concept. So here we have a graph of what looks like a line, but it's really a rational function that had a hole in it, a removable discontinuity. So if I asked you to evaluate the function at c, like this particular number, before today you just would have said, like, it doesn't exist. There's a discontinuity, or there's a hole, or a removable discontinuity. Well, today we're going to ask you to estimate the limit as your function, as your x values approach that value. So what are you trying to get close to? And algebraically we'll see a couple of them, and then most of the time we're going to be using our graphing calculator, either the graph itself or the table feature. So even though there is a hole here in the graph, I could estimate on either side of that discontinuity and determine if the limit exists. So here's a good representation of what it looks like when you are on your table. So for this particular function, negative 3x plus 1, that's just a linear function. There are no discontinuities in a linear function, so this is kind of goofy, but they went ahead and they used a table and they put it in ask mode, and they didn't actually evaluate it at 2 for some reason. I don't know why, but they didn't. So they pretended like they couldn't plug in 2, is what's going on. Excuse me. Alright, there we go. Come on, pen. See, even my technology is tired today. There we go. Alright, I'm going to pause for a minute, try to get my pen to work. Alright, everything's working. So, pretend you can't actually plug in 2. You can't evaluate it at 2. So, they went into ask mode and they used 1.9, 1.99, 1.999, and then they went on the other side of 2 and did, it doesn't have to be symmetrical like they did, but just something slightly above 2, slightly below 2. And if you look at the output values, it seems to be like they're getting really, really, really close to a certain number, and they're trying to approach the number negative 5. Well, turns out that's exactly the value when you plug in a 2 into this function. Negative 3 times 2 plus 1 is negative 5. So this is a case where if I was asking you to evaluate the limit, the first thing I would do is try that number. And if it actually exists at that number, then you have your answer. But sometimes we're going to find out today that the numbers don't really exist there, like this example here. If I'm asking you to plug in a 3 to this function, well, this is a rational function, and look at what's going to happen if you plug in a 3 right here in the denominator. You're going to get a divide by 0, so it doesn't exist. This is one of those removable discontinuities we talked about back in the day. So there's a hole right here. So your job is to figure out, disregarding the area where the hole is, what are we trying to approach? What are we trying to get to as far as the y value? So on your table, you could have plugged in something on either side of 3, and you do want to check both sides. So 2.9, 2.999, and then also 3.1, 3.001, and they're getting really, really close to the same number. They're really, really, really close to the number 6. So even though it technically does not exist at x equals 3, the function is approaching the value of 6 when you are trying x equals, I think this is a typo, I think it's supposed to be 3. There we go. So it's getting close to the number 6. That's the idea. This is what we're going to do in our table. We're going to put it in ask mode, and then I'm going to choose numbers that are very, very close to the number I'm trying to find on either side of it. It's very important that you check either side of it, because we're going to find out that sometimes it is approaching one value on the left side and a different value on the right side. Those are called one-sided limits, but we'll talk about that in a moment. All right, here. Independence of limit from function value at a point. Okay. So these two graphs are showing you that when you try to actually plug in the number c, the function itself is undefined. That's that removable discontinuity idea. But the limit does exist. So that's the big key difference today. While the function is not defined at the value, I can give you an estimate from the idea of what's called a limit. And then here, if you don't have a removable discontinuity and it's just a smooth function like this, or any discontinuity, then not only does the limit exist, but the function is also defined. So you can have any of those cases, right? I mean, this is kind of cool. See how there's like a random point up here? So the function is defined, doesn't match the limit though, so we'll talk about what that looks like and what the answer is in a moment. I said the wrong thing. Sorry, I didn't realize there was a point up there. All right, the limit is a y value, a very key feature. Sometimes kids get confused as to like what are they supposed to write down for our answer. And you're going to tell me what value the function is approaching, which is inherently a y value. So here's our one-sided limit idea. One-sided limits refer to just approaching from the left or from the right of a value. So if you see a notation where there's a little negative sign above, like as a exponent-looking thing almost, that means they're wanting you to pick numbers that are slightly below the value of c. So if I was doing like as x approaches 3 with a negative, that means I'm supposed to be picking numbers that are only below 3, but close to 3. So like 2.999, 2.99999. The thing you don't want to do, though, is go on the other side of 3. If it's a one-sided limit, you only pick the side that they're asking you about. So same thing with the plus sign. That means numbers that are slightly above that value. So 3 plus would be 3.001, things like that. So watch for that little notation. I feel like the older I get, the more bifocal moments I have. I got to read really carefully. And there's a section of your paper coming up in one of your notes where what's on paper, like you can't read anything, even if you're young like you guys. So when we do the lesson, my slides are very clear as to what it's saying, so you're going to have to just kind of write over the very blurry text that's on your worksheet. All right, so one-sided limits. Okay, and then we have a two-sided limit. So if the function is approaching the same value from the left and from the right, then you have what's called a two-sided limit. And that's the typical type of limits that you're going to see. If it doesn't have any notation up at the top here, plus or minus, they're implying that it's a two-sided limit, and they want you to test both left and right side. So keep that in mind. Let's look at some examples. So finally, I think we're finally getting to your notes. Here we go. We have what's called a step function on your notes. And step functions are full of discontinuities. They have jumps, they have holes, they have all sorts of weird stuff. So if I'm trying to approach the function, if I'm trying to approach 2, the x value of 2, but from the left side, so here's 2, right? So if I go straight up, there's a hole, but if I go to the left, that is a y value of 1. But if you go to the right side of 2, so over here, all of a sudden it jumps up to 3. So what that tells us is that since the left side and the right side do not approach the same value, that the limit does not exist for this one. Okay, so for a two-sided limit, for this function, approaching 2, the limit does not exist. It does have one-sided functions, limits, but not two-sided. At least not at that value. All right, this one is not on your notes. We're going to skip ahead to one that's on your notes. Let's take a look at, oh, I shouldn't have skipped that. This is important. All right, here's another example of how one-sided limits might exist, but two-sided do not. So right here, as we're approaching 0, if you're approaching 0 from the left side, your function, is going down. Remember, end behavior is 0, going down. And then on the right side of 0, it's going up, going to positive infinity. So because they approach two different values, if you want to call it that, infinity and negative infinity, the limit does not actually exist for a two-sided limit. So if the left side and right side differ, you can't tell me that the limit exists. That's an example of that. And this is always fun. This is called oscillation. Now, I know our college algebra book calls it an oscillation. It looks like your book does as well. If you see this happening, and it happens a lot with trig functions, it's going to bounce between values over and over and over again. So you have to really look at the graph, especially on trig functions, because sometimes kids are just looking at the table and then they plug in a number and they're like, oh, I got an answer. Well, you have to be careful, because if that number toggles or oscillates, you can't tell me that the limit exists. All right. So here, for these examples from your textbook, estimate each limit if it exists. So as we're approaching 0, it's a little hard to tell in this pixelated picture, but actually I don't know what it's even showing. I think there's some oscillation going here, so we wouldn't, I don't know, I'd have to get a better picture on that one, guys, and I'm going to skip that question for now. This one does have a smooth feature, though. It is approaching 0. So don't feel like every time you have a trig one, it's going to say it does not exist because it's oscillating. That's not really true. So reasons why limits at a point do not exist. If they approach from a different value, that's a key one. So that's you'll see jumps, or you'll see asymptotes that go in opposite directions. If it increases or decreases without bound, this is a little confusing because in calculus, the way they word the questions, they might tell you that the limit doesn't actually exist, but they're still going to ask you what the function approaches. So really it's an end behavior question. And then oscillation is a big one. So jumps, holes, asymptotes that don't go in the same direction, that's what we're looking for. All right, so here, somebody graphed this for me. That was nice. And this is what it looks like when you graph it. So, fun. We have a jump. So at 0, but it says this little plus sign. So they want you to approach 0 from the right side. So right here, it looks like it's approaching 1, 2, 3. However, from the left side, it's not approaching that same value. So if they asked me for a two-sided limit, then I would have to say it does not exist. Here we have another one-sided limit. We're approaching -2, but from the left side. So here's -2. And from the left side, the function is going up, 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 up. So what they want you to say is that the function approaches, and you can write the word or you can just put an arrow, that it approaches infinity because it's going up forever. So that's the key here, guys. They're not asking me like, does the limit exist? They're asking me to estimate it because of the way the limit is notated. So keep that in mind. All right, here. Man, Hoffpower's the best. She already put all these screenshots on for me. I don't even have to grab my calculator. So here we have what looks like a line, but we know from experience that this is a rational function that has a hole in it. Remember, you would have factored these, x plus 5 times x minus 2, and then saw that there is a removable discontinuity at x minus 2. So apparently at x equals 2, there is a hole. You just can't see it on your calculator. But look what happens on your calculator when you try the table. It gives you an error because it's not defined at the value for 2. So they tried, and remember this is two-sided this time, so they have to try numbers both to the left and to the right, and it seems to be approaching 7. So that is our limit. 7. All right, here we have another set of discontinuities. We have some vertical asymptotes here, and this is a two-sided limit. We want you to figure out the value as x approaches 3. So 1, 2, 3 is this guy right here. And here's our problem. On the left side of 3, so that'd be the 2.9s, it's approaching negative infinity apparently. And on the right side of 3, they're getting big, big, big. They're approaching positive infinity. So because they're approaching two different values from each side of that x value, the limit does not exist. And that's what you write. Had they changed that to a one-sided limit, we would have had a different answer. All right, number 5. Thanks, Hoffbauer, for graphing this for me. Now, don't get confused with the fact that there's an asymptote. That does not mean a vertical asymptote. That does not mean that the limit doesn't exist. Like, for instance, here. What your calc teacher is going to want you to notice is that both sides of -2, they're both approaching positive infinity. So that's what we're going to write down, that because of this notation for the limit, that your function's approaching positive infinity. And then, let's see, at 4, let's have one of those discontinuities again. There's a hole at 4. You just can't see it, but I noticed on my table when I tried to plug in a 4, and that's the first thing I try on all the limit questions. If I'm not sure, I just try plugging it in, and if it gives me an error, then I know I have a discontinuity. And we do check both left and right side. It seems to be approaching the value of 8. Okay, -1 from the left side. So there is a vertical asymptote, but because it's a one-sided limit, they want you to look at the left side of -1, and it seems to be going down, down, down forever. So you're going to say your function is approaching, or the limit is approaching negative infinity. All right, what else? It looks like there's one more here. Oh, same function, but this time we're approaching it from the right. So on the right side, it's going up, 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 so it's approaching infinity. Again, don't get caught up in does the limit exist or not in this section. I'm just asking you to evaluate the limit given whatever notation I've done. So one-sided limits, you can always tell me something. Two-sided limits, sometimes the answer is the limit does not exist. All right, infinite limits. These are fun. Basically, they're just end behavior questions. Like, we've already done these a lot. So I'm asking you what happens when your x values get really, really big, so really far to the right, and then when your x values get really, really small or go really far to the left. So it's just end behavior, guys. Nothing fancy. Let's look at some questions. Oh, watch out for oscillation again, but oscillation does not mean infinite limits don't exist, so we got to kind of explore that a little more. There's a nice little chart here of rules, but I just want to review some old ideas for you, if you wouldn't mind. This is an infinite limit. They want my x to go really far to the right or really big, and this is a rational function. This is that top-heavy, bottom-heavy equal weight concept. You are welcome to go to your table and start plugging in gigantic numbers. You can look at the graph, but we're going to find out that those old rules of top-heavy and bottom-heavy and equal weight still apply. This is a bottom-heavy rational equation, or expression, which means when I plug in really large numbers, my end behavior, my asymptote, exists, it approaches 0. Remember that guy? The horizontal asymptote will be at 0. So when you look at the graph, you see the function is doing exactly that. It's approaching 0. And when I look at the table, as my x's get bigger and bigger and bigger, they're just getting smaller and smaller, but they're gonna approach 0. Remember, they're not really going to get to 0, but that's okay. That's the point of limits. It's approaching 0. So if I notice that I have an expression that I have familiarity with, like a rational expression that we did a lot of work with last semester, I'm just going to use my end behavior rules. So this is an equal weight fraction, which means the horizontal asymptote is just the coefficients. So there's going to be a horizontal asymptote at 2, which means when I plug in really, really large or really, really small numbers, my value is going to come out to 2, or approach 2, I should say. So we are going to answer it just that way, 2. All right, similar idea, different function though. We still have an equal weight fraction, so the coefficients are -3/1. So your horizontal asymptote is at -3, which means that's what my limit is going to approach. Could have done that with a graph or a table as well. All right, trig. Makes me nervous. But I do know kind of what this looks like. It's one of those cosine curves. This is what it looks like in particular. Mrs. Hoffbauer graphed it for us. Thank you. And you see all this oscillation going on, right? So as I approach infinity, as I keep traveling to the right, it keeps toggling between y values, and it will never really settle on 1. So this is a case where the infinite limit does not exist. And then, and you can write yourself a little note here that it oscillates. I don't know if I spelled that right. There's 2 L's in there. It looks weird. Okay, here we have another rational function. I notice it is bottom heavy. More x's in the bottom. So that means your horizontal asymptote is going to bottom out at 0. I can see that on the graph and the table. So as my x's get really big, my function is approaching 0. So that's kind of nice that an old topic comes back, and that's why we kept using the words, end behavior, the end behavior, the horizontal asymptote is the end behavior, because we were waiting for this moment right here for it all to come together. All right, this one, when you graph it, which, oh, it's right here. All right, there we go. Here's the graph, and they want to know as your x's travel to the left. So you notice this guy just keeps heading down, 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 down. So what we're going to say is that it approaches, the function approaches negative infinity because it's traveling down forever. So really, it's just an end behavior question. And notice on your table, it starts to go scientific notation on you, but that's just a really, really, really negative number. Like, it's just going to keep adding zeros to the end of it. Oh, trig. They graphed it for me. Now, trig makes me nervous because of the oscillation, but this time they want me to approach when x equals 0. So that would be here, from the left and from the right. It's not an infinite one. And it seems to be approaching this value right here, which I'm guessing is a 2. So when I go to look at the table, and I try to plug in numbers that are on both sides of 0, so something slightly negative, slightly positive, we are getting an approach of 2. I snuck in a non-infinite one there. Be careful. Alright, bacteria growth. Remember this guy? And that cool formula from back in the day? They wanted me to graph this between 0 and 20, I don't know if it's hours, yeah. So I'm going to pretend like I graphed it. Oh, Mrs. Hoffbauer already did. Look, she's wonderful. So that's what it looks like. And we set up our window, we typed it in carefully, and then they wanted us to estimate how much bacteria is present after 8 hours. So I just went ahead and plugged, or she did, but I would have done it too. I would have just plugged in an 8 because that's not a discontinuity. So that's actually the answer. They wanted me to use the graph, but whatever. We got technology, so 3.736. But remember, this is number of bacteria, or grams. So you have to kind of decide where you want to round. It's not bacteria, I'm sorry. Well, it's grams of bacteria. That's extra gross. Okay, estimate the limit as t gets really, really big. So I started plugging in really, really big numbers, and I noticed it kind of flattened out to 4. That's that logarithmic growth looking stuff. So it is approaching 4. Oops, that was this answer down here. Because if you think about like physical space, like there's only so much bacteria that can grow, can only hold so much. So life finds a way and all from Jurassic Park. Alright, so moving along, car estimation. Is the value of a car. It starts at 30,000. They modeled it for us. I think there's a T up here behind that. And they want me to graph it and then estimate it. So here's the graph, and it looks like an exponential decay, which it is. And then I do want to estimate after 10 years. Well, I'm just going to plug in 10 and get that. It's not a lot of money. All right. Really depreciated, I suppose. So then they want me to estimate as time increases to like forever. Well, obviously you're not going to have a car forever, but look what happens to the value of the car. At some point, the car is going to be worth nothing. So it's approaching 0. And that makes sense. Like, it's not actually going to go negative. You can't have a negative value of a car. And at some point, the car is just literally worthless or useless to you. Alright. This assignment, none of you can read on your worksheet. So what we're going to have to do is basically, well, it is from your textbook, so you could just look at your textbook. But in class, I'll probably have these just sitting up on the screen so you guys can work on this during class while we have some dead days here while all this AP testing is going on. So pause the video, jot these down so you can actually read them. And then, same thing here, pause the video, maybe just do these questions. And then, pause the video one more time, get those guys done. I know you can't read them on your paper. And one more for the road. Internet video. Things going viral. I love this question because is this not the truth? Alright. Adios, amigos. We're done.